served as a board member in other positions. He's a webmaster. He's the head of the Astronomical League. He does a tremendous amount of work, coordinator, whatever. It's a tremendous amount of work he puts in for the club behind the scenes. And it's kind of silly for me to introduce him, really, because he could be up here saying it better than I can. But anyway, he's a man of many talents and interests. And tonight he's going to talk about the alternatives to the Big Bang Theory, and he has already available up there for you.
Jonathan,
Okay, Jonathan?
you want to get one of the lights down, I think.
One of them's already down.
Okay.
There's not that many pretty pictures. Here, I'll turn off the lights and you can look at this pretty picture. Alright, so the Big Bang Theory is a subject of a lot of muttering even to this day. And I thought it would be interesting to look into alternatives to it because there's a lot of people who still say that they don't believe in it, and there is the very idea of it is just really hard for people's brains to process. So I don't know that this presentation will help your brains process it any more easily, but I'll do my best. So, to give you an overview of what we'll be talking tonight, we're going to talk about what the Big Bang Theory is, what it isn't, what the Big Bang Theory has predicted, what known problems there are with the models proposed by the Big Bang Theory, what alternative models have been proposed to the Big Bang Theory, and how can we test everything that we talk about. All right, so the Big Bang is what's called the Standard Cosmology now, and so you may hear the standard model of the atom. This is the astrophysical cosmological equivalent of that. It's the default that everyone's understanding. Everyone in science, when they talk about the evolution of the universe and the history of the universe, this is the standard against which they're basing their work. So it makes predictions that we can test, and it explains, its models describe things that we observe. So that's the point of a model. So, graphically speaking, this is sort of a line through time. So we have this singularity here where everything breaks down. We have this long period of action that we can model mathematically, but we can't look at. And starting in the early 1980s, we got our first look as far back as anyone had ever seen, to 380,000 years after the Big Bang. And we'll talk about what this patch of blue and green is in a little bit. So we go through a period of darkness, which is not to say inactivity, and then stars are born, and almost immediately, and that's 400 million years on past it, almost immediately we have the universe that we're used to living in and looking at through our telescopes. So, and then you get into dark energy and what's called the lambda-cdm model, where a lot of research is still being done to explain why we don't see as much matter as we would expect to see, and why we see expansion of the universe continuing to accelerate. We'll talk about that a little bit less, but we'll cover it. So, in the beginning, the Big Bang doesn't talk about the beginning. The Big Bang model is exclusively about things that we might have some chance of reproducing in the laboratory, some chance that we might be able to observe them someday, even if we can't look at them now. So the singularity, fading into what's called the Planck epoch, is something we can't look at. So I've put in red things that, I put that in red because it's not really included in the Big Bang. One of the most common objections to the Big Bang is, well, what started the Big Bang? That is not actually a part of the Big Bang model. So it's a very interesting topic. When you start talking about that topic, you start getting into string theory and brane theory, but all of it is prior to what we can look at. It's prior to what we can measure. And it's ultimately, currently at least, maybe not forever, but right now, not really in the realm of science. It's more in the realm of mathematics and speculation. So the grand unification epoch is where we start to, it starts to get into the realm of, we can observe effects from that we would see in the future. The electroweak epoch is as far back as we've gotten in the laboratory. And then inflation is something we'll talk about quite a bit later in the presentation because it's not included in the classical model of the Big Bang. So after the very early universe, which, I have a typo here, this should go to -12. And this kicked out the poor quarks. So this should be -12 and this should be -12. So quarks, the fundamental particles of matter formed, and the fundamental particles of light and quarks, leptons, and other strange things that we have to go to Switzerland to see. And then finally, atoms started forming. We started getting chemical elements, and then finally started. So we'll go through each of these pretty quickly. So the Planck epoch is the tail end of the singularity. You say, what's before the Planck epoch in the singularity? What caused the singularity? The Big Bang model doesn't go into it at all. It is simply the point at which all of the equations that work for the rest of time stop working. You get, if you take these equations all the way back to the beginning of time, you end up with a temperature which is 1.4 times 10 to the 32nd power Kelvin, which just is not a number that the human brain can process. Trillions of degrees Celsius. You have a density so that, for all your analogies of a teaspoon of a neutron star weighing 20 tons or 100 tons, this bears no, you could have galaxies on a teaspoon. So the common model calls for gravity to be part of one super force with all of the other fundamental forces we know. And I'll give you, so the four fundamental forces that we have today are the electromagnetic force, which includes light, radiation, etc. The weak nuclear force that holds, that produces chemical bonds. The strong nuclear force that holds the components of the nucleus of an atom together, and then gravity. And gravity breaks off in the era where our equations don't really work, which is why if you've heard about people talking about the grand unified theory and completely uniting the forces, nobody has really made that combination work on paper and make everything else work at the same time. So up here we'll split off gravity. We get to the grand unification epoch. So that's as far back as mathematics has compellingly got you. It allows you to put the strong nuclear force together with the electromagnetic force and weak nuclear force. You still have a temperature that can't be made sense of. You have more than 10 to the 27th Kelvin. Way too hot to form any quarks, way too hot for any matter to exist. It's just a ball of energy at this point. So in the electroweak epoch, which is 10 to the minus 36 seconds, lasting all the way to 10 to the minus 12 seconds, still a fraction of a fraction, the strong nuclear force breaks apart, and we get to the electroweak force. What people are so excited about the Higgs boson being produced in the lab at CERN is that that actually took our laboratory experiments all the way back to the electroweak epoch. This is finally a temperature, pressure, and energy level with which we can actually do something in the laboratory. So from this point forward, the Big Bang is something you can do in the laboratory. So that takes us all the way up to here. Up down to temperatures of 10 to the 15th Kelvin, where each particle, where the fundamental energy level of particles is 100 giga-electron volts. So past that point, we can start forming quarks. The electromagnetic and weak nuclear force separate. The Higgs mechanism turns on, and that's when you start seeing mass. That's when particles start having mass. Because the Higgs boson is thought to be what produces, what allows mass to exist, but it doesn't have mass itself. At that point, there's still no atoms, there are still no electrons. Actually, electrons start to form during this period, towards the end of this period, but mostly it's quarks and gluons. And it's way too hot for baryons, which are ordinary protons and neutrons and antiprotons and antineutrons, to exist. And too hot for any of the two quarks. Basically, you can't stick quarks together at this time. It's too energetic. The quarks are escaping. In the Hadron epoch, that's when you actually can start gluing quarks together and having protons and so you actually start having matter and antimatter. So that takes us all the way down here when the quarks get put in jails of the fundamental nuclear particles. So everything is still pitch black. There is too much activity happening for photons to actually travel. And that continues on for quite a long time. So basically, matter and antimatter combine and annihilate each other. And we're left with a faint dusting of protons, neutrons, and electrons, and eventually photons dominate the energy of the universe. However, it's still too hot for it to be transparent. Light is still not traveling at this point. It actually takes to 10 to the 10th seconds for the universe to cool down to the point at which light can start yes. So I think I missed that. So nuclei start forming. Hydrogen and helium nuclei start forming out of protons and neutrons, and from that point, matter dominates. So at this point, it's still too the universe is still too energetic for the nuclei of atoms to hold on to any electrons, but it's getting there. So starting at around 100,000 years after the Big Bang, hydrogen and helium atoms start to form, and protons pretty much all get captured as part of atoms. You don't have free protons floating around in the universe past this point. However, because hydrogen and helium atoms, because there are still a lot of free nuclei floating around, not all these nuclei have captured electrons at this point. Since there are all of these charged nuclei floating around, it basically immobilizes photons and prevents light from traveling around the universe. And what you get is kind of what the weather looked like this afternoon, which is a dense hot fog where nothing can really move. And however, this allows for pressure waves to start to emerge that it is thought sets up the large-scale structure of the universe later on. So 100 million years on from the beginning of the Big Bang, the universe becomes transparent, and that's where the earliest light that we can see comes from. Now, the cosmic microwave background radiation is the sort of the heat signature of that swamp at 380,000 years after the Big Bang. So you see structures start to emerge, and including this cold, dense spot that's on this cold, completely empty spot that is on the cover of Scientific American this month. And this is as far back as science can look. And anyone who looked at a TV set back in the days when we had static on, when we had analog TVs, has seen the cosmic microwave background radiation. A significant component, about 1% of the static that you had on your screen on your old CRT TV sets was this energy. So you have seen the beginning of the era of atoms. So in the stellar era, everything gets normal. Stars form, galaxies, galaxy clusters, and superclusters form, and they condense along lines. If you've seen, I think I have an illustration later on, but if you've seen sort of the spider webs of galactic clusters throughout space, you've seen basically you've seen them collapse along the same lines that were there in the primitive swamp of nuclei and leptons. So at this point, everything in the universe is simply hydrogen and helium. You have nothing else but light elements. The first generation of stars starts making lithium, and it actually takes early supernovas to start creating any heavier elements. And several generations of stars later, you get us. So, part of the current model of the galaxy, of our galaxy in the case of dark matter, and of our universe in the case of dark energy, are two factors that account for the rotation rates of galaxies. Why, for instance, why we see galaxies rotate as one solid disk rather than the centers rotating faster than the edges. And dark energy explains the reason that we see the expansion of the universe continuing to accelerate. It's sort of, you can kind of think of it as, it has the same effect as anti-gravity, but we have no models for that. So this is actually both of these are sort of a liability of the Big Bang model as it currently exists, and we'll get into some attempts to take those into account in a bit. So what does the Big Bang model predict that we can test? Well, the Big Bang model partly came out of the observations of Edwin Hubble and Besto Slipher and Henrietta Leavitt, who saw that the distances that in the case of Leavitt, that stars were actually receding from us, that other galaxies were actually receding from us, because that is not something you expect to see in a universe that is static and where everywhere is similar and time is infinite and space is infinite, where there wasn't ever a beginning. So the Hubble's law is sort of the actual observational underpinnings of the Big Bang model. Other people had kind of suggested models that look like the Big Bang as thought experiments, but nobody had any evidence to support it. Hubble actually put all the pieces together and produced a graph showing the universe, further galaxies receding away from us faster than nearer galaxies. So it predicts the cosmic microwave background radiation. It correctly predicts the approximate abundances of light elements, which is the stumbling point of pretty much all the alternatives I'll talk about later on. And it also predicts a cosmic neutrino background that has not yet been measured. That's why everyone is so intent on, this is why everyone is building neutrino detection chambers way below the surface of the Earth. Because if we can find the cosmic neutrino background, it's one more strong prediction the Big Bang makes that will allow us to be more comfortable that all the pieces sort of work together. So just to get back to the diagram. So problems with the Big Bang. There are several issues that the Big Bang presented. The flatness problem, the horizon problem, the monopole problem, the baryon problem. I ended up moving this into a different model, but into a different section. And the existence, the necessity of dark energy and dark matter. So this symbol is lambda, so it's lambda-cdm. So lambda is dark energy, and CDM is cold dark matter. So somebody, Alan Guth and several of his friends in 1981 got to talking about a mathematical model they could apply to the Big Bang to solve two of those problems at once. If you just took the size of the galaxy and inflated it by about 10 to the 50th power times, almost instantaneously, from 10 to the minus 35th to 10 to the minus 32nd seconds in the electroweek epoch, you right away take care of two of the problems. So expansion, so inflation suggests that you go from practically a singularity to almost the size of the galaxy almost right away, or almost the size of the current universe right away. And expansion can be very slow after that point. So to give a different model, with the standard model of the Big Bang, you have to keep going way, way back. With the inflationary model, you start from a very tiny singularity and inflate it almost instantaneously, and then have a very regular, you have a nice linear curve after that point. So, what does this solve? So one of the problems that we talked about was the horizon problem. The horizon problem is that if the galaxy is 13.7 or 13.8 billion years old, I keep saying galaxy, if the universe is 13.8 billion years old, then one side of the universe is 27 billion miles from, 27 billion light years from the other side of the universe. And yet, the cosmic microwave background radiation is within 0.01%. Every spot is within 0.01% from everywhere else. So that actually violates the information, the correlation to the this light speed limit, which is that information can't travel faster than light either. So you can't have the outcome of a large system be that similar everywhere unless all of that volume, all of the particles in that volume can interact with each other. You would start to see discrepancies. So inflation fixes this problem by taking an incredibly small volume and inflating it super big so that virtually for the entire cosmos, the initial conditions are the same. There's another model called variable speed of light that we'll get to towards the end. There's another big problem called the flatness problem. So if we have a closed universe, then we'll eventually have a big crunch where eventually gravity overwhelms everything else and everything gets pulled back into a singularity. If we have an open universe, then eventually the cosmological constant or dark energy wins and everything rips apart really fast and recedes from everything else. If, on the other hand, we have a flat universe, then you see a very steady inflation or a very steady expansion happen virtually forever. You don't get a huge discontinuity like these models. But the flatness of the universe that we see now is such that 1 second after the Big Bang, it had to have been flat to 1 part in 10 to the 14th power, which is just an alarmingly large degree of precision. It either tells you that maybe lots of Big Bangs have happened and there's never been humans to observe it, which seems awfully self-centered, and we don't like self-centered things in science. We don't like really weird things that we happen to be part of, because every time we thought we were the center of the universe, it's turned out that it really wasn't that way. So with incredible precision comes a lot of suspicion. So the way that inflation solves this, inflation sort of demands it, because you inflate space in all directions equally by 10 to the 50th power times. And the initial condition of that tiny volume that inflation inflates doesn't have to be nearly as precise for things to get flat. The inflation, mathematically speaking, actually enforces extreme flatness, even if the initial muck was very non-flat. Inflation makes it flat, and it kind of accidentally solved one of the other problems, the monopole problem, which is in the era in which the strong nuclear force was united with the weak nuclear force and the electromagnetic force. Their condition should have been created that monopole particles should have been produced, which would be a charged particle. So normally, I might have to go Dave Bailey, but normally if you have a magnet, you have a north pole and a south pole, and all of the field lines have to run out of the north pole and into the south pole. All of those fields have to be closed loops. In a monopole, you have a charged particle that just basically radiates out magnetism in all directions, and you don't have to have a closed loop there. And so the mathematical models of a grand unified universe suggest that they should have been produced all over the place in that time period, and we've never seen a single one. But inflation says that even if you produced a lot in that tiny volume and then inflated that volume to 10 to the 50th times instead of making it linear all the way back to an earlier time, you can create a bunch of monopoles in that tiny little volume, but then in the inflated universe, they're still extremely rare, and you wouldn't expect to ever meet them. And so that is a nice thing that falls out of inflation. So what else does inflation predict? It predicts large-scale structure formation. It predicts mathematically the anisotropy that was seen in the Kobe probe, so we've had different cosmic background explorers since the discovery in New Jersey of the cosmic microwave background radiation. We had the Kobe probe in the early 80s, WMAP in the 90s, and now Planck, which is still active. It also predicts gravitational waves in certain orientations, what's called B-mode polarization. If you remember all the fuss at the, I think, about 12 in the news episodes we had about the Bicep 2 saga, Bicep 2 claimed that they put out rumors for about 6 months that they found B-mode polarization in the cosmic microwave background radiation from their observatory down in Antarctica. And finally they, a long time later, released their observations, and it turned out that they had stolen a screenshot from from another team's presentation at a conference. They had actually taken a photograph of it and used that as the data that they fed into their model, and ended up reproducing, I think, the magnetic polarization of dust in the Milky Way, I think is what it ended up being, or maybe dust in the solar system. It was it was one of those embarrassing moments like the faster than light neutrinos at CERN. So far, large-scale structure formation and anisotropy actually work out. On the other hand, inflation is sort of designed to solve these problems. One of the things that people object to in inflation is that if you don't like the universe that it produces, you just tweak it a little bit until you arrive at a universe that looks like the one we live in. And there's no good explanations for any of the dials you can turn on inflation. So people don't like, dials that you can turn without having any reason to be turning them other than you're trying to fit the data better. It reminds people a lot of epicycles. So you start to see people talking about, modern day Ptolemies turning their epicycles in the inflation world. One other problem that inflation doesn't help at all with is the baryon problem. Baryons, again, are protons and neutrons, are matter. So if the universe started out with approximately equal matter and antimatter, as it should have by models, why do we only see matter in any significant quantity today? We see positrons, and that's about it. So is there a physical explanation? Is there some asymmetry in the way the weak nuclear force works that actually favors matter when they collide? Are we living in a region of the universe that is dominated by matter, and are there other areas that are dominated by antimatter? We'll actually come back to an alternative to the Big Bang that has a similar philosophy. And then there's the electric dipole moment, and basically I don't really know what that is either. If you see an electric dipole moment, it biases things towards our matter rather than antimatter. But so far there have been some pretty compelling experiments supporting number one. In practice, we still don't have a theoretical explanation for why the weak nuclear force would be imbalanced that way. So what you've all been waiting for, alternative models. So again, inflation isn't an alternative model to the Big Bang, it's just an add-on to it that makes the observed data match makes the theory match the observed data a lot better. So let's start looking at the alternative models. Well, as you may be aware, the Big Bang was not the first model anyone had ever made of the universe. Before the Big Bang, everyone sort of thought the universe was static. not long before the Big Bang was proposed by Georges Lemaitre in the 1930s, there was still an active debate, the great debate between Shapley and
Curtis.
and
Heber Curtis.
Curtis over whether the Milky Way was the entire galaxy or whether
Entire universe.
the entire universe rather, or whether the other galaxies that we saw were actually separate island universes like our own. And so the fact that the Big Bang was proposed less than 20 years after the Great Debate tells you that our knowledge of the cosmos was inflating at about the same rate that the Big Bang did. But the static universe model continued to be sort of the default. So everyone saw that a spatially and temporally infinite universe was not the direction that things were heading. General relativity caused problems for that because with space, with gravity being proposed as a curvature of space, there's no way you can have this without having everything collapse. And there's no reason for us to have these beautiful galaxies. Everything should just be falling in on each other constantly. There's the temporally infinite but spatially finite universe, which is actually the one that Einstein favored for a long time, and it's hard to say in late life what he really believed. He was not a Big Bang supporter at all. What he said to Lemaitre to his face in 1932 was, "Your mathematics is correct, but your cosmology is horrifying." So the static universe is not an expanding universe, and the static universe is a universe in which no new matter is created. Now, if you have a universe that requires new matter to be created, it sort of violates that whole second law of thermodynamics thing. So we have an alternative to the static universe that tries to take into account the observations of Edwin Hubble and what we were starting to learn about the universe, what's called the steady state model. It's temporally infinite, it goes on forever, it doesn't have a beginning, and it's similar everywhere at all times. It is to take into account the Hubble's law of expanding. However, if you can't have it expand and keep the same amount of matter, because then the density of matter is continually dropping, and then we shouldn't exist. Nothing should exist. All the matter should just be flying away from each other. So in the steady state model, new matter has to, one way or another, continually pop into existence to keep the density constant so the universe can be similar everywhere at all times. So that was the model supported by Fred Hoyle, the man who coined the term Big Bang. He denied that he meant it, that he was trying to insult it when he called it that, but unfortunately, as you saw, the Big Bang isn't really an explosion. There's not really any explosion going on at all. It's really a cooling down. It's an anti-bang. But his term for it stuck. He really didn't like the Big Bang because the Big Bang seemed to him like a creation story, and he was a very militant atheist, and he just couldn't stomach the idea of this Belgian priest proposing this primordial egg hatching and becoming the universe at some finite point in the past. That sounded too much like Genesis to him. And so he went basically the rest of his career trying to find alternatives to the Big Bang, continually developing the steady state model. There's one disciple of his that is actually still active today, an Indian cosmologist. Redshift quantization is another steady state universe. If you've ever heard of Halton Arp, the ship Arp, the man who made the ARP catalog of peculiar galaxies. ARP's world was a world of observing galaxies with very large telescopes, and he kept seeing these weird things where there was this little galaxy back here and a big galaxy back here, and their redshifts were different, and he just couldn't believe the Hubble law. And then he discovered quasars, and quasars have redshifts that nobody could understand. Redshifts that suggest that they were moving away from us at a rate that just couldn't be dealt with by any theory at that time. And so he got into his head the idea that redshift was some kind of fundamental intrinsic property of certain types of matter. And so the Hartman universe is one in which active galactic nuclei continually spit out these quasi-stellar objects called quasars. Now, if you remember what a quasar is in the modern understanding, as has been confirmed by observing lots and lots of quasars and looking at them throughout the universe, a quasar actually is in a galaxy with an extremely active galactic nucleus. So pretty much this is one of the cases where somebody's actual visual imagination that based on their actual at the eyepiece observing kind of took over any critical analysis they had of whether their universe made sense. And Chip Arp actually held on to this belief until he died in 2013. No matter how much more data we collected about quasars, he just never could give up this idea. And the documentation about the redshift quantization model basically says this entire line of reasoning died with Chip Arp.
But if you...
So one thing that redshift quantization suggests that you should see regular lines, you should see very rigid lines because all these redshifts should come in at even quanta, which is what they were seeing in the early observations. But in reality, this is the map of all the known quasars. This is where those spiderweb galaxy, those spiderweb 3D representations of the universe and of galactic clusters come from. You have this very, very random, and you have large scale structure, but there's not quanta, there are not vertical lines there. Yes?
I was going to say, but I thought his daughter remained a defender.
Say what?
I thought Arp's daughter was the last defender of it.
That could be, but I don't think he was still getting published in his later years. And I don't.
My understanding is if you say things negative about it and she finds out,
She'll let you know.
yeah.
Well, I guess I may be getting some nasty comments on YouTube in the near future. Tired light was proposed by Fritz Zwicky. Fritz Zwicky proposed a lot of interesting things. It suggests that some factor, it was an alternative explanation for redshift. Redshift was not being caused by the actual physical recession of distant galaxies from us. It was really being caused by photons slowing down as they traveled through space, either because there was some kind of ether in space that slowed down photons, or because maybe there were some kind of physical fields that slowed them down. Period light is totally dead.
I don't know if I'd say that. I would
light,
not say that.
If light slowed down, then anything distant would get blurry, and the further away it was, the more blurry it would get. If it were caused by physical fields in space that photons passed through, you would see a smearing of the entire distant sky, which we don't see. We don't see in the cosmic microwave.
There's a lot of different models. You have a simplified model, and there's a lot of alternatives. So
It also It also
There are a lot,
suggests.
you can do the same little Band-Aid thing by saying, oh, you got an inflation model. There's a lot of different ways of looking at what underlies a tired light model, and it can evolve from numerous different computational models, not just the one that you're representing. So there's more diversity than
So-
what you're suggesting.
So tired light suggests that photons slow down as they travel through space. And that
That's
the
a s-
universe is not actually 13.7 billion years old, and that it is not actually 27 billion light years across.
So
So
again,
there's
it's a little bit of a
observations
simplification.
that support.
Is this a debate or a presentation?
So the other thing that tired light can't show is the actual measured redshifts of supernovae and other galaxies. In the tired light model, if everything is approximately the same distance, we should basically, so what happens is as supernovae that are further away from us actually seem to last longer on an actual linear line with their distance away from us. So the width factor is how long the supernova lasts, the redshift is how far away from us, is how fast they're moving away from us, which is the classical Doppler effect. In the tired light model, we would expect to see a straight line, a straight horizontal line. And we would expect, if they were not receding from us, they would last the same amount of time. So it's really a difficult one to get over. Now, varying speed of light is not tired light. It's not an alternative to the Big Bang. It's actually in addition to the Big Bang model. What it tries to do is replace inflation. It instead of taking space and inflating it by 50 orders of magnitude, it suggests that in the early universe, light traveled at 50 orders of magnitude faster than it does now. It's an interesting idea. At this stage, it's more of a thought experiment. What it doesn't get you is, it doesn't get you solution. It does solve the flatness problem, and it does solve the horizon problem. I don't think it really does anything with the monopole problem, and it doesn't really predict the anisotropy that we see in looking at the cosmic microwave background radiation. There was another hypothesis by Paul Dirac, another notable character of 20th century physics and mathematics. Dirac noticed that he kept seeing these to the minus 40, to the 40 terms popping up in the equations that he was working on, and it struck him as strange. And so he produced this model of the universe where gravity was inversely proportional to the universe's age. So basically, as the universe got older, gravity got stronger. Gravity got weaker, rather. And also, the mass got, basically, as the universe got older, the mass actually increased according to the square of the age of the universe. So it's an interesting hypothesis. Pretty much even his closest friends looked at it and said, yeah, I don't know what we can do with this, and nobody besides him ever has really touched it. You hear about modified Newtonian dynamics a lot. It is also not an alternative to the Big Bang. It's an alternative to the lambda-cdm model. And the idea with modified Newtonian dynamics is that you don't need dark energy and dark matter to explain the rotation of galaxies, and MON produces a really nice, realistic rotation rate of galaxies. It doesn't explain gravitational lensing at all, and so that's one, and it basically can't explain what we see in the bullet cluster. The bullet cluster is another big win for the dark matter group. So dark matter and MOND explain rotation of galaxies equally well, but dark matter explains gravitational lensing. On the other hand, you have a different alternative to the lambda-cdm model, which is the tensor vector scalar gravity model. And it does explain gravitational lensing, but it doesn't explain large-scale structure and isotropies. So you can either explain one of them with this or the other with this, but so I don't know that there's any way of uniting them and really producing an alternative to dark energy and dark matter. There's also loop quantum gravity, and loop quantum gravity is really when you're starting to get into the pre-Big Bang, the stuff that is not part of the Big Bang, and it underlies some of the cosmologies that go before the Big Bang. So loop quantum cosmology is a cosmology you can build on top of loop quantum gravity that claims to get rid of the singularity of the Big Bang and produce a big bounce that happens on a periodic basis. This is not super well funded. It's reasonably popular right now, but there are not that many people working on it, and a lot of loop quantum cosmology seems to be more of a demonstration model at this point than something that's being really taken seriously.
Do you know what underlies it?
So loop quantum gravity is, so it basically is an attempt to take quantum physics and start building gravity that can interact with it. Because in the standard cosmology, quantum behavior and general relativity don't meaningfully interact.
Do you know any idea of how they interact within that model?
In loop quantum gravity,
Yeah.
did it one time, but I'm only a layman, but I am currently not remembering that side of it very well. But if you'd like to talk about it afterwards, I'd be happy. The aquatic universe is one model that starts with the big crunch before the Big Bang. The cyclical universe postulates a periodic big crunch, so basically an ongoing series of big bangs and big crunches. They started out with the string theory, brains, extra dimensions basis, but more and more work is being done on them using the physical universe that we observe. They both make a prediction about that is testable. They predict no B-mode polarization in the cosmic microwave background radiation. Inflation postulates that there is B-mode polarization. So BICEP has, the sort of failure of BICEP has given a little boost to this group of theorists. It at least has reduced the expected strength of B-mode polarization, and it's pushing it down towards zero. So it tries to avoid the singularity too by having the continuous collapse. And then finally, for the purposes of tonight, there is the plasma universe, originally postulated by a plasma physicist named Alfvén in 1966, Nobel Prize winner. Picked up in the early 90s by Eric Lerner and popularized in this book. It assumes an actual static universe where the universe is filled with an ambiplasma of a mixture of matter and antimatter. And you may remember we were talking about the baryon problem. It also, that's what it kind of specializes in. It specializes in the idea that we live in a mostly baryon pocket. There are other pockets that are mostly antimatter, but we don't. but there was no Big Bang, there's no expanding universe. Unfortunately, it doesn't really predict any of the other stuff that we see happen and that we can measure. It doesn't predict the cosmic background radiation, doesn't predict Hubble's law, it doesn't predict the abundances of light elements. Another thing that tired light doesn't do. And it predicts large amounts of high energy photons, which is not something that we have so far observed. So those are your alternatives that are currently, those are the ones that have gained significant critical support. And then beyond that, you tend to get into religion. So rather than go there, I think I'll go to more questions. Yes, sir.
Previous slide to questions, it showed the timeline.
Yes.
It's shaped like a cone.
Yes.
Is that just for display purposes, or can we assume that the Big Bang is like shot out of a gun, so you have a cone effect, or is it like one explosion where it's...
So this curve, this is really nicely done. This is from the WMAP team, but so this is the team that produced this particular map. But this shows inflation happening, and it also shows the effect of dark energy. So the
Right.
idea is that dark energy, if the universe were totally flat, it would expand out forever, but dark energy seems to be accelerating the expansion, and it's not known whether it's enough to actually produce a big rip, which is where dark energy takes over and everything disappears from each other. That is one of the, it is pretty popular that as the universe ages, individual galaxy clusters will lose sight of every other galaxy cluster.
No, but just the formation shooting from left to right. As it
Yeah.
expands, it goes from, the timeline
Right,
goes from left
yes,
to right.
Yep.
Why wouldn't the timeline go from the center of your quantum fluctuations up also? Why does it go from left to right?
I think it's just to produce an easy, it's just so that they can put lines on it pretty much.
Okay,
I mean,
so in other
in
words,
reality, you know, the Big Bang doesn't happen from a place. You know, we're in the center of the universe. Everywhere in the universe is in the center of the universe in the Big Bang. There's no center of the universe.
that's what's confusing.
Right, but it is, I mean, so it is confusing. It's not really something that,
Well,
I don't
that
think it-
graph is streaking it through time, so
Right, so
you've got
this
a
is-
two-dimensional representation of a three-dimensional universe dragged out through the time dimension. So yeah, it's
Right.
all screwed up, but it's
Right.
just so you can see it.
Okay.
yes,
Okay, if you're on your Big Bang theory,
uh-huh.
why would we get galaxies colliding with each other? Everything's expanding at the same rate.
So in a galaxy cluster, gravity takes over from, so dark energy is what pulls galaxy clusters apart from one another. If they're not close enough together to combine, they'll get pulled apart by dark energy. People are not comfortable with dark energy. People are desperate for an alternative to dark energy. But so far, haven't found it, and it just keeps creeping there in observations. But inside a galaxy cluster, gravity actually dominates, and so gravity will pull galaxies together. But so we're going to, you know, eventually merge with the Andromeda galaxy. We're never going to merge with, we're not going to merge with the stuff out in Coma. All of that stuff is eventually going to disappear from our sky. Yes.
What are your sources for this information?
Lots of, so the Lawrence Krauss book, the Timothy Ferris, the whole shebang book.
So you can go back to the different areas and
So I
and
have
look
read
into
like
depth
the
into
Guth,
them.
I've read the Guth paper, I've read the Hubble paper.
So the Big Bang paper is not necessarily the alternative model papers?
I have read some of ARP's papers. I've looked at, actually Eric Lerner has all of his papers published on his website. So I actually have, in fact, I read, there's an interesting manifesto from basically physicists opposed to the Big Bang. They got Eric Lerner and some of ARP's progeny and some of Hoyle's progeny, intellectual progeny, got together, I think, 30 signatories on the original manifesto against the Big Bang, and it's up on, if you search for Eric J. Lerner, he has the original manifesto posted on his website, and it is interesting reading, but it is not intended to be a scholarly paper. It's more of a cry from the heart of you all think you're so smart and you think that everyone else is so stupid. But, so it's worth reading. They're definitely incredibly smart people. I mean, all of these models are well beyond my my mathematics capabilities. I pretty much stopped at differential equations. So, yes, sir.
Where you see the multiverse, where the multiverse?
So multiverses also are way outside the
Yeah.
bound of the Big Bang.
You brought in
multiverses. So one of the things that people like about loop, I think one of the things people like, I think it's loop quantum gravity that avoids having a multiverse thing. I'm blanking, sorry, but so certain, especially additions, the Big Bang doesn't deal in what happens before the Big Bang. The Big Bang theory is just an attempt to explain from our earliest understanding of particle physics to the present day, and what we can observe, what has happened so far. It doesn't go beyond the singularity. So, yes.
I think there are certain modifications of Guth's inflationary model.
Right. The original.
The
Yes.
original model where they predicted this way through the universe, that you have multiple big bangs, you know, and we have this constant splitting somehow or other of the subsequent in time, and so you end up with many little universes. The universe in a sense
Yeah.
is contained area like we have.
Yeah. So one of the additions to inflation is that inflation never stopped. One of the additions to the inflationary model is that there are mini inflations happening all over the universe, and the problem with those is that I don't think there's really a test that's been proposed for detecting them. So it's definitely an interesting theory. Guth is still very active. One of the interesting things is that the original Guth inflation paper is pretty much, there were some mistakes that he made that really the inflation that we use now is a more recent, I think 1997 even, formulation of it that corrects. The paper was by two people that yes.
No, we're
Okay.
quite a bit over the time limit,
All right.
unfortunately. One last question.
All right. Thank you.
All right, so clearly we have a lot that we could keep talking about this particular subject, but we will have to
Also a
relocate.
strong desire to drink some beer.
Yeah, we will have to relocate to the one Coney Island I'm aware of where you can get a beer. That is their National Coney Island on Van Dyke Road, just north of 12 Mile, where we can all take this up in a less academic setting. We are here, of course, as the guests of Macomb Community College, and they let us in here during the summer when they're normally closed, so please take your trash, cups, chips, anything like that. Let's make sure that that's all out of the room before we leave. And thank you very much for joining us tonight.